Well, hello everyone. It's my pleasure to be here again and to see all of you. My name is Boris Larin. My colleagues and I will share with you the story which happened to us last year. We call it Operation Triangulation. What is it? This is a targeted attack on Apple mobile devices, on iPhones. Okay, what makes it remarkable? They used a previously unknown piece of software, and they used a string from exploits of 0-day. And this was background infection without any user interaction. So here's the phone, which is there, and it is infected by advanced spy software. We identified it also at the Kaspersky Lab. Okay, today we'll share with you all the technical details of this, I think, most sophisticated attack ever identified by the Kaspersky Lab. We'll tell you how we managed to see, catch, and analyze all the elements of this attack. We'll also share with you the details of all vulnerabilities and how the malicious code was remotely executed. We'll talk about their way to go around the pack. Also talk about the core vulnerability, and we'll also talk about the way they managed to go around the Apple processor hardware protection. We'll also talk about the spy software they used for this attack. I'll give the floor to my colleague, Leonid, who will share with you the details of how this was identified and discovered. Hello. Hello, everyone. I hope you can hear me. People make mistakes. And there's hackers behind this attack also made a mistake. And thanks to their mistakes, we managed to unearth all the elements of the kill chain. And that's exactly what we are going to be talking about. This started with suspicious network activity. We have a corporate Wi-Fi network for mobile devices. And on one day, when monitoring this device using our CM solution, we found... Mic, is the mic fine? Boris, your mic is on. Okay, so we're monitoring this network, saw that some iOS devices are connecting a set of domains which don't look suspicious. They were two-word domains, and they had the COM high-level domain, and this was in pairs. So they had the first domain with several connections, and then you had regular connections with the second stage domain. And the first stage domain was used as an exploitation server, and the second one was used as the command server. They had high traffic. They were all registered with N-chip and secured by Cloudflare. But then we saw some other signs of infection. The device was connecting to the iMessage server to download some attachments. Then it's connected to the first stage domain several times. Often it was a backup rabbit.com, and then they regularly connected the second stage domains. Then we understood that this was an iMessage payload, which was the vector of attack. So we understand that the devices of our staff are being infected. We need to run an investigation. So what did we start doing? We started running around and collecting the devices. At that time, we didn't know what the malicious software could do. So we had to explain it to the owners of the devices that we needed to investigate them so that we don't scare the wrongdoers off. Okay, we collected the devices, we have them. What shall we do next? It's not exactly clear because for these versions we didn't have any good forensic tools. And the only way to do it would be to make backups of these devices and have a look at these backups. So that's what we did. We used the mobile verification toolkit to analyze these backups, and then we started having a look at the picture. The first thing to understand was that the wrongdoers were deleting their traces pretty well. They had thought a lot about the kill chain and made the attack very difficult to identify. So this malicious attachment went to the device and they deleted it, but they forgot one thing. They forgot deleting the folder where this attachment was held. So in the logs we can see a folder, it's empty, it's modified when they go to the domain, but there is no any attachment there. And then it turned out that they deleted a lot of data from the SQL bases which write logs. And they store different data, and so they deleted a lot of data, but they forgot about deleting data from the data usage SQLite. So this is the network traffic statistics based on processes, and so thanks to this we saw a suspicious process with a lot of outgoing traffic. It is called backup agent. Well, backup agent is legitimate, but the first fact is that it is deprecated, meaning it's not used starting with iOS 4, and it shouldn't use the network. So this is especially suspicious, and this was our first tool. We published it at GitHub. We called it, I think, Triangle Check or something like that, to check whether your device has been infected. Okay, we know that this device is infected by triangulation. Okay, how to get the payloads? It's not clear. So we started looking for some methods. So we know that the infection vector is the iMessage attachment. And we tried to use the Google Project Zero technique to intercept the iMessage with the Mac. So you can launch Frida, you can also have a look at the iMessage and dump the message. So we had to modify the X script because we needed to go further than the text message. So we referenced the binaries in the iMessage, we understood how it was done. Okay, so we can dump our messages, so we can set the router, the TV, and so we have launched our scripts. We can dump our messages. We authorize with the accounts, and we are waiting for the new infection. But this didn't work out. Why? Maybe we had some race condition. Maybe the message couldn't make it to the Mac, but the payload wasn't found this way. Okay, let's proceed. We couldn't see the man-in-the-middle attack. We tried to use another catch here. All the traffic went through the SSL, and we tried to do some SSL pinning to play the man-in-the-middle attack. For this, we launched the server with the VPN, regard with a proxy. We deleted our SSL certificates and gave them to the target devices, so the whole traffic should go through the server, and we could leave decrypted traffic using a proxy. As a result, we learned how to read the whole connect between the infected device and the server, and even patch the code, patch the data coming from the server to the device. We even coded a Telegram bot to respond to the new infections, to see how much data goes where, and to monitor these infections. So the first connect we got was not encrypted at all. It was a plain text HTML page with JavaScript, which was a validator, which done a lot of checks, and one of them was like that. It built a yellow triangle and counted its hash sum, like fingerprinting, and this was sent to the server. This was the reason why we called it triangulation. And it turned out, in one of the modules for geolocation, they also used triangulation. So we have two hits with one stone here. Okay, after this, we used open key cryptography, but the problem was that all the keys were stored in memory. We cannot read the memory, and how to get the keys, well, this was something we couldn't do. We decided to find a workaround, and for this we moved the encryption logic from the payload to bit proxy, or we swapped the keys when we could. This way our encryption ran on the mid-add-on script, which was 400 lines long, and round after round it decrypted the strings we needed, and we received payloads continuously. And then we had to debug the script offline. So we, well, when we added some more script, we had to wait for a new infection to see whether the script works or not. So this is the debugging in progress. So with these steps repeated again and again, we received validator exploits, spy software, plugins, and so on. And as a result, we got all the components of the skill chain. And Boris and Georgy, my two colleagues, will share with you the details of this. Okay, they used attachment in the iMessage, and there was a PDF file there, and they had the TrueType exploit inside of it. I'm confident that you have all seen this format, because this is the most widely spread type, developed in 1991 by Apple. Then they shared this technology and the code with Microsoft. It added this code to Windows 3.1, and well, there were a lot of vulnerabilities discovered there in Windows through this, and as a well, these fonts have the microscripts for the virtual machine to type. The exploit was written in this language. I had to analyze it, to disassemble all these virtual instructions to see what they were doing. I read the documentation. It turned out that there were a lot of unclear things there, but I tried to develop my module for the IDA Pro tool, so that I don't deal only with the text dump, but with the graphs and so on, to automate it in a way. As a result, I decided to reverse engineer the TrueType VM code on iOS. I found quickly a processor for these instructions, and I found one undocumented instruction which wasn't mentioned anywhere. I read the Apple documents, the Microsoft documents, they describe all the instructions, but for this one, I tried to Google it, I couldn't find anything, and the only place where I could find some information on this were some old source codes from Windows. That's the only time when they were mentioned there in this document. So there is a code which doesn't do anything, but they say that it is only available for Apple. And this code, this source code, so this all dates back to the early 1990s. So we have an undocumented instruction for Apple only. So I think you can guess where the vulnerability is for this remote code running. So here you can see the CVE for this. There are two interesting parts here. They're almost identical. To the left, they align some points, so they bring them to the end, and then the other one does the same, but they start from the end and go back to the beginning. And the developer of this code must have coded something for aligning the points starting from the end, from the beginning to the end, and then he just copy-pasted it and changed this a little bit, but then he must have made a huge mistake, because the point goes beyond the point buffer, so the endpoint equals the size of this buffer. So he should have deducted 1. And this gives the threat actors a chance to add data to another buffer, which is adjacent to this one, and it has offsets for other arrays. And as a result, these threat actors can obtain control over memory. And this code dates back to the early 90s. And it's easy to exploit, just like many browsers of the 1990s. I will not talk too much about exploiting this, but let me share with you a few words about the way Apple fixed this. So this code was there from the 1990s, and then this code was deleted in January 2023, and we know that the wrongdoers had been exploiting this by that time. And Apple deleted this only from the latest versions, iOS 16 and Mac OS 13. But iOS 15 and Mac OS 12, which was still supported at that time, still had this code. So this vulnerability was still there. Okay, I don't know why. Why Apple decided to delete this instruction abruptly. Maybe they started receiving a lot of notifications on some issues, on breakdowns, and it's good that they fixed it, but it's not good that they didn't tell anyone about it. So usually when companies know about active exploits, they publish patches and they notify everyone that they should install it, because this is an actively exploited vulnerability, and this is something they didn't do. Well, they exploit this with the new models of phones. They needed more vulnerabilities, because in the ARM64E processor you have some hardware protection called pointer authentication code, and all these pointers in the upper bits have like a signature, and if there is a mismatch, then the phone is reloaded or rebooted. And they need to bypass it. And they used these vulnerabilities. Number one, there were too many pointers which were assigned by the Pakiza instruction, which is set as default. So you assigned everything with a zero identifier, and they can be these pointers can be easily found in the memory. Okay, what do the wrongdoers do? They find the signed pointer for the DLL SIM function. This way you can get a signed address for any function. So they use it for the mprotect function to change the rights or privileges. Then they make the match O header for the file, which has an expert, which is related to another function which is not usually exported. It's in another module and can be used to sign any pointer with any key and any identifier. So the attackers initiate this header in the list of loaded modules, and then they get a chance to sign anything they want to go around the bar, the pack. And then they use all this to do the NS expression. In Objective-C, there are some classes. They are called NS expression and NS predicate. And this is actually something like SQL. This is a script language designed for queries. But it is quite flexible, and you can use this language for anything. You can run any function, you can run cycles and conditions, so you can do anything. But all this code should be packaged in one big expression, and that's exactly what this bad actors were doing. They used a matryoshka of these expressions, about 3 of them, kind of embedded one into another, and the final stage was to run the JavaScript exploit. So for this, for JavaScript, developers can use specific libraries, but they don't have the just-in-time compilation mode as developers. And these hackers still use it a lot. They modify the environment of this library by modifying the memory, and they get what you can see in this screen. So they give this engine a lot of memory. They also remove, or they switch off garbage collection. They disable exclusions, and they switch on the $VM mode, which is a special debugging mode, which is only available for the developers of this engine, but you can still turn it on. And this way, in this mode, you can use really strong functions from the JavaScript interpreter. For instance, one of them gives you the address of any object and the type of it and so on. Some other functions let you modify the memory, and the hackers used it all to modify the memory from within the interpreter. Well, I've been with this business for about 10 years. I've been looking for many, and I have found many exploits. I have published a lot of 0 days in Google Chrome, Microsoft, and so on, but dozens of them. But this case has been the most sophisticated JavaScript exploit ever. It was obfuscated with a RFIDS obfuscation tool, and this way they reduced the size of the script and encrypted it. And this script had 11,000 code lines after this, and most of it was about running any native functions directly from the script. Well, how did they manage to do this? They used the JavaScript callback object, and they use it together with a long chain of gadgets and the operator instance self. And this system let them run a lot of functions with a lot of arguments and receive responses to these functions. Now I'd like to talk about the core vulnerability. Well, I think that this is a really strong vulnerability, and but these vulnerabilities are few and far between. What makes it so powerful? Well, you can easily, without having to manipulate the memory in a stable mode, get access to physical memory from the user level. And this vulnerability was in the syscalls responsible for memory mapping. So these are crucial components of any operating system. The XNU has a syscall which makes a memory entry. It has many input parameters. It also has the size of the memory and the offset for the record or for the entry. And then this can be mapped with another syscall using vmap. And this syscall creating memory entry had a check for the offsets and sizes. And this check is easy to bypass. You can bypass it with the size and offset you can see here, and as a result, the hackers can have a memory entry with a huge size covering all the address space you can have.
The next syscall that helps exploit this record had the following check, and it doesn't check for the fact that there might be a memory record with the large size that I mentioned previously. As a result, the adversaries can refer to user-level objects that are outside the original object that was supposed to be initially mapped. And if this method is used with a certain physical object, the adversaries can map the physical memory. This is the diagram of a physical map of iPhones. There's an area with hardware registries, there's DRAM, there's VRAM, there's the flash memory, and in the video memory, a special object is created, purple GFX mem, that's a video buffer essentially. And it can be used together with a syscall, and adversaries use that. And this gives them full access to physical memory, and from the lower level they can address any physical addresses. They can either read or write any physical addresses. Here you can see all the steps of the exploit. To be able to read core memory. First, the perpetrators create this purple GFX mem, then they get the address, and various heuristics are used for various phone models. Ultimately, it helps the perpetrators to read the physical memory using physical addresses. They find input or iboot handoff. That is an entity that remains in the physical memory after the iBoot, a bootloader in a MacBook or iPhone, and it contains a map of various memory regions on the physical level. And the adversary gets the DRAM address and the memory ranges, the core codes and hardware registers. They find CPU data structures for each CPU and also find a VM page array. They create a stream and get its address from CPU active thread. And then they can get a physical address to the stream from VM page array. Then they can read any core addresses.
С помощью физического примитива в эту структуру потока. Очень мощная уязвимость.
That's a very powerful vulnerability.
Все равно она не сравнится со следующей уязвимостью, которую я хочу.
But it can't compare with the next one that they want to talk about.
Собственно, по моему мнению, жизнь хакера,
In my opinion, the life of an iOS hacker is quite a miserable one,
на самом деле
because
очень сложно.
breaking an iPhone is very difficult.
Судить сами, злоумышленникам нужно удаленное выполнение кода, потом им нужно
They have to do remote code execution, then they have to
дальше нужна уязвимость ядра,
bypass the PAC
на других системах на
to
да.
explore the kernel vulnerability. And when they have this in other systems, such as Windows-based systems, they can do whatever they can with the system. But here they have to confront the final bosses. They have to bypass PPL, KTRR, and kernel pack. What are these abbreviations? PPL is a page protection layer. That's a special protection.
Когда у злоумышленников есть уже полный доступ к ядру,
When adversaries have full access to kernel, they cannot do much exciting. They cannot initiate any code. They cannot initiate a malware.
важные ядерные структуры.
And they cannot initiate important kernel structures because they are protected by that structure. KTRR prevents the override of the kernel executable codes, and kernel pack is the same protection but for the kernel. Bypassing these protections are very difficult, these hardware protections. But it turns out that in Apple chips there's a feature that helps completely bypass these sophisticated hardware protections, and it makes the life of an adversary again very happy. It turned out that in the new versions of Apple chips, ARM64, there's a special hardware function that helps work around the hardware protection and write data in a protected address. For that, you've got to write the required address, the required data, and also something that is very similar to a hash into the hardware registries of an iPhone. The central Apple chip is not just a CPU, but also a few peripheral devices, and this slide enumerates just some of them. All of these abbreviations, each of them is a separate device which sits on the crystal of an Apple chip. And the CPU works with all these devices using the special registry that exists in the memory. The way it is done, that in the memory there's a particular area. If something is written to particular addresses, something else can be read in other memory addresses. And that's how the system operates all of these devices that decode cryptography, that decodes audio, etc. A description of all of these addresses are stored on Apple devices in special files that are called device trees. It's a binary file that you can parse, and here you can see an example of how this tree can be parsed. This is a range of addresses for a CPU. The size of the area and the address of the area in the physical memory. The exploit used these 6 mystery addresses. You can see them in the screen now. I checked various device trees for various Apple devices, for various patches, and I couldn't find a single mention of these addresses. Then I checked various kernel images. I checked various kernels for various patches. I reversed the patches and peripherals, and I couldn't find a single mention of these addresses. Then, by trial and error, I found out that these are also available in M1 and M2 chip devices in MacBooks. They are also available, but they are not used either. I used a special tool that, using virtualization, can get access to particular addresses, and there were no links to those addresses, it turned out. Question becomes, so how do adversaries use these addresses that are not documented anywhere? And also, what device sits behind those addresses, and why it has such powerful opportunities to bypass protections? Let's think logically and see what devices sit next to those addresses. And it turned out that a good candidate was the GPU coprocessor. Here you can see how this looks in the memory. The areas that are exploited are very close to well-known areas of the GPU coprocessor. So let's see how they are used. The first address is only used at the beginning. At the end, it sits in a different area compared to the others. And here you can see the code that was used to exploit this register. And I assumed that this was used to turn this device on and off, or to work with interrupts. And I decided to look at working with interruptions, and I found the meaning of this registry very quickly. There's a special debugging block core site developed by ARM, but it's also present in Apple processors. The source code has descriptions of using with the main kernel of the CPU, but the code on the left does exactly the same. So it's safe to assume that the code does the same, that we are still dealing with the core side, but for the GPU coprocessor kernel. And that solves one part of the problem. But let's look at other addresses. The first one is used to work with interruptions. The two other addresses are most likely used to turn on and off this feature, because they are only used at the beginning and end. There's one other address, but it's only used in the newer versions of chips. And the two final addresses are the most exciting. The first one receives something that very much looks like flags, and the final address receives data itself and something very similar to hash. Here's how it looks all together. And notably, the data that is written has to be aligned in blocks of 40 bytes. You can see that they're written sequentially in the same register, and once the code is executed, the data just appears in the memory area that should be protected. So what could be done with this vulnerability, with this hardware feature? You can change records in the page table, you can change data in the protected segment PPL data, and you can change code. The code would work for some time, but then an exception would kick in. And a quote-unquote hash Here's how it looks. Initially, we thought
такой очень ламерский
but
кастомный алгоритм.
that was some
Он делает, он XORит
newbie algorithm that seems to XOR the data
найти эту таблицу.
from some table. We tried to find such a table, and we have quite a big file collection, but we didn't see any mention of that. That was something custom built. So it turned out that it was not a hash, it was something different. It was much closer to the checksum. It was an error correction, more accurately the Hamming code with a unique search table. And initially I thought that this feature
напрямую в память в обход
can write directly to memory, bypassing hardware protection, but we got a prompt from the community that this fact points to the fact that with 99 probability, this feature helps write data directly, not into memory, but into cache. So most likely that's a debugging function for cache. Okay, so we have been able thus to solve this puzzle. But still, this looks like a very unusual vulnerability. And it is not clear how the adversaries came to know how to use this hardware function. And here you can see what the adversaries had to know. That this function existed, that the Hamming code was required to use it. They needed to know the unique values in the table. They also importantly needed to know the place and purpose of all the MMIO registries and also the procedure in which to work with them. And interesting how Apple fixed this vulnerability. Within the device, there's a table that describes all prohibited address areas, and here's how it looks. The address, the size, the type, and the tag. The tag is not used anywhere. That's just a comment of why, of what that is and why it's blocked. And the exceptions are quite straightforward. PCI, it's clearly why you block access to PCI. Dart and DAPF are special table addresses that can filter references to registries. Also clear why they blocked. SMMU is a memory management unit. That's memory controller. Also logical to have access to it restricted. And here's how Apple mitigated this vulnerability. And here you can see that this time the description is not self-explanatory. Okay, I have explained to you about a kernel exploit, and at this point the adversaries can do whatever they can. They can have full control of the device, initiate malware or whatever, a full, completely remote, and without the any actions of the user. And here's what they do. They initiate a malware, initiate a payload that does artifact clearing. And what they do with the payload initiated in Safari, they make Safari follow the link that the adversaries provide in their exploit. Safari follows the link and receives a JavaScript that verifies the victim. If that is the victim, then there's a new exploit which is 0-day for Safari. And upon this 0-day exploit, there's a further exploit on the kernel with a totally different code than the one that was in the JavaScript, a binary code, but using the same vulnerabilities. And then the adversaries once again verify that that is the target victim, and only then they send the final payload. The adversaries use this exploit, even though this interim exploit, even though it's not necessary, to obfuscate to divert attention from the final payload. And now my colleague will continue talking about the malware. Hi everyone. You would appreciate that components that are sent to the device also contain a lot of interesting things. Let's look at the validator, for example. If we look at the code, we can see that it carries out some actions according to the list. And interestingly, the adversaries leave the names of the actions in the code. And you can see that it clears the logs and the exploit traces and also gathers information about the device. Regarding the log clearing, they are cleared only for particular processes. If we look at the list of those processes on the screen, we can see that they relate to iMessage and the components that are needed for browsing web pages. We can also see that the traces of the malware message is removed. For that, the adversaries use the SMSDB database that stores information on all messages received by the device. And for every message, they look up the Apple ID of the sender, calculating the MD5 cache, which is compared to the table. If there's a match, there's a malware message, and it has to be removed. The perpetrators didn't make a wise decision to keep those 40 hashes in the code, because with enough time, you can break those caches and to identify which Apple IDs were used for attacks. And this is what we do. We were able to restore most of the addresses that were held by the perpetrators. And of course, we sent information about those to Apple so that they could follow more closely the activity from those accounts. Upon clearing up traces, the validator checks if there's a jailbreak installed on the device. The validator can determine more than 10 types of jailbreaks. Moreover, the validator checks whether the device has software that were jailbroken, such as Cydia or Frida. And during the exploits, there's also a check whether Corellium is used. Corellium is a virtual platform that helps launch iOS on the cloud. We have been able to find another curious action, PSP detect, and it was never called in the code. The essence of it was to check whether the device had certain files. However, in all configurations of the validators that we had, the list of files was empty. So it was a mystery why this action was needed. To uncover this mystery, we decided to proceed from the name of the action, the PSP detect. When we think about PSP, the first thing that we imagine is PlayStation Portable, a gaming console that was possible decades ago. So why would adversaries want to check for a PSP on an iPhone? Do they really want to understand whether the victim plays computer games? But it turns out that PSP abbreviation is also used in computer security, and that's a personal security product, or essentially an antivirus. However, many of you would know that there are no antiviruses on iPhones. However, there are. So the conclusion is that this code worked not just for iPhones and iPads, but also for MacBooks. It validated and gathers information about the infected device, Apple ID, the phone number, the device name, and many other data points. All of this information is sent to the adversary's server. And this helps establish whether that is the victim that they want to infect. And if the infection happened properly, then there's an APT framework loaded onto the device, which we called TriangleDB. We determined that TriangleDB can be launched on iOS versions that were published for about a decade ago. The framework is meant for cyber spying. It gathers photographs, audio from the microphone, contacts from the address books and passwords. And TriangleDB gets information about Apple devices that are nearby the infected device. We also identified plugins that extract information from WhatsApp, iMessage, and Telegram. The plugins are quite curious ones. Let's look at, for example, the audio from the microphone. The audio contains both the encoded sounds and the metadata that's happened during the audio recording. The module also records the sound only when the screen is off. This gives the victim fewer chances to understand that they're being tapped. And when listening to my talk about plugins, you could have imagined that a lot of information, gigabytes of data, is gathered from the infected iPhones. But the question becomes, how can the adversaries process such large amounts of data quickly? When we attend this conference, we make a lot of photographs, and here on PH Days we have a lot of places where you want to make a photograph. So how do adversaries understand what photographs are useful and what are not? For that, they use Apple's AI, and let me show you how this is done. When we make a photograph on the iPhone and we save it in the gallery, it is processed by a neural engine. This engine extracts information on the objects that are shown on the photograph. For example, look at this picture. The engine understands that it shows coconuts, a beach, sand, etc. And it can also extract text. For example, the neural engine finds the word beach on the coconuts. The engine can also find animals and analyze documents. The adversaries take all of this information and upload it onto their servers, and they use these descriptions to understand what they need and what they don't need. And by the way, this is the first case when a malware uses machine learning. I believe this idea of abusing Apple's AI is just great. Okay, this brings us to the end of our presentation, and here are some conclusions that we would like to share. Gather and check network logs at work and at home. it's easier than you think. We made a few presentations previously on how this could be done. This is our recommendation. Please do that. Second, hardware protection means, even if they are state-of-the-art, they are quite useful in front of an APT attack if they can be bypassed. And this can be taken into account when you choose the device that you want to use. And finally, thanks to machine learning, malware, sadly, would soon know everything about the victims of the devices which it would infiltrate. You may have heard reports about the recently announced OMS technology called recall. I'm confident that adversaries would use that. And that's it from us. Thank you very much.